Welcome to Walkabout the Galaxy, the unstoppable astronomy podcast where the science is universal, the opinions are personal, and the sponsor is Physicsal.
You don't need that.
Yeah.
I liked unstoppable, though. I like that we're unstoppable.
We are
Physicsal?
Unstoppable. Physicsal.
Yeah.
Having to do
Josh
with
is bad
physics.
at English if you're new to the program.
I've heard that.
I'm unwell at English.
Right.
Jeez, Jim. Learn some grammar. We are Strange and Top, the astroquarks, also known as Josh Cole and Jim Cooney, coming to you from the Walkabout Studios at the University of Central Florida. Charm Quark is on assignment, but we're happy to welcome to the show UCF planetary scientist Stephanie Jarmak. Stephanie, thanks for joining us today.
Thank you for having me.
Be sure to stick around at the end of the episode so you can hear me remind you to follow us on Facebook and Twitter and YouTube and something called the Internet.
Wow.
Our stumpers are interstellar.
All right.
You ready?
The movie?
I knew you would think that.
Yeah.
But
The answer is yes. It's a good movie.
Interstellar adjacent.
Okay.
No, this is real interstellar.
Okay.
Yeah.
Even better.
Jim, I1 Oumuamua or I2 Borisov?
Wow.
That's
You
hard.
stumped. That's the sound of Top Quark being
Definitely.
stumped.
Well,
Definitely.
I2. Definitely I2. For the following reason. I1, Oumuamua, was super fast and went right through the system before we had a really good chance to take a lot of good measurements.
But it was shaped like a needle, and
It
it's an
was.
interplanetary spacecraft.
It's definitely an
So we
alien
can't
spacecraft.
send a mission there, you don't think?
Can't send a mission there. Can't study it. Not going to know any more about it than we know already.
Yes.
But
That's
the other
really
one,
lame.
I2, we saw it early enough that it's still got
still
months
on
left of visibility for professional astronomers. So we're going to learn lots more about it. That's pretty badass.
Right.
Pardon my
This object we talked about on our last episode is the most recently discovered interstellar object to be coming through the solar system. Seems to be a comet that formed around some other star at
Right.
some point and is paying us a visit.
Right.
So-
So that's pretty cool. It'd be like it's going to be really interesting to see. I guess you guys talked about this already in the last one, but like
No, I didn't.
we know it's interstellar because of its orbit, but then if we get good looks at its spectrum, like we could see how comets from other solar systems differ from comets from our solar system or something like that. I don't know. I think it's be cool.
We have coming up a little bit later some of the first measurements. So now telescopes are being trained on this thing, so we have some first
Nice.
measurements of this thing. We can talk a little bit about that. Stephanie, your stumper, you may not know what these terms even mean, so it may be particularly stumping.
I probably don't.
I did not know what one of
I'm a
these
lowly
was.
graduate student.
No, you're a high graduate student.
That's right. Yes,
I'm
one of
not-
our, one of our
I'm
more
very
senior
sober
graduate
right now.
students.
Yeah.
You're very what?
I'm very sober.
You're
right
not
now.
too high.
Yeah.
But you're not lowly for certain. You've got like 9 jobs already lined up for
Yeah,
after you graduate
absolutely.
from
Yeah,
here.
that's all I did at DPS. Yes.
Yeah, so Stephanie has been globetrotting this year and has got more sort of like invited international speaking engagements in her last year of grad school than I've had my whole career,
Nice.
as far as I can tell. So,
Nice. The student becomes the teacher.
yes, eyeball planets or snowball planets.
Eyeball planets or snowball planets?
Yeah.
I have not heard of either of these.
Really don't know about snowball Earth.
Snowball Earth. I mean, okay, I have heard of Snowball Earth.
What's
I just
snowball?
wasn't thinking about
What's
it.
snowball Earth?
Snowball Earth was when, I guess, a period of time during the Earth's formation history when it was very cold. Right?
How did she figure that one out?
I know.
This is why.
Graduate
This is why
student.
she's one of our top students.
Exactly. Yeah.
No, so the in fact we have evidence that twice in the Earth's history it was all the water on the surface was solid.
That's solid base.
Once maybe 650 million years ago or so, and another time maybe about 2.5 billion years ago.
Mhm.
And how, you might ask, did it stop becoming a snowball planet? Do you know? I'm looking at Top Quark.
No, I don't know.
You don't know? You don't talk about this in the in intro astronomy?
I don't. I'm very intrigued about how you would figure that out, that the Earth was solid, frozen solid 2-something billion years ago.
Oh.
But you don't have to tell me that.
Conditions
You
of the
just have
solar
to.
system at that time, maybe?
Sorry?
The conditions of the solar system at that time, maybe, would
Well,
be...
that's just theoretical.
No,
Yeah.
there is observational evidence or
Evidence?
data from the Earth's geological history that supports that,
Mhm.
but I don't have the details on that. However, 630 million years ago is a little bit easier nut to crack than the 2.5 billion. But the planet still has heat in its interior, which drives volcanic activity, so eventually you bust out enough CO2 from volcanic explosions. Right. So you kick in some sweet greenhouse warming and melt those things. And then
the greenhouse effect is good then.
It is. We're loving, because we have enough. If we didn't have any right now, we'd be sad.
Yeah.
That's true.
Anyway, that's Snowball Planet.
Okay.
Do you know what an eyeball planet is?
An eyeball planet. No, not at all.
Not at all?
Not even.
I didn't know what it was either. But when you think about it, if you think most of our exoplanets are tidally locked to their star, that means that they're so close to the sun that they're orbiting, to the star they're orbiting, that they keep the same face pointed towards the star, just like the moon keeps the same face pointed towards us. So
always looking at it.
Yeah, but imagine it's a watery sort of world like the Earth, and it was tidally locked. What would the day side be like compared to the night side? I'm actually asking.
Okay, no, I am thinking about it.
Yeah. Right.
Well, I mean, it would some of that water, depending on the temperature on that side, would evaporate potentially, but it depends also on the wind. Well, it wouldn't really. Yeah, the atmosphere circulation would sort of redistribute heat.
Yeah, the dark side would be frozen, and the light side would not.
So maybe the day side would be liquid. So maybe you have an ocean on the day side and ice on the dark side, and then you see this beautiful reflection of the sun of the star in the day side ocean, like an eyeball.
Wow.
Staring back at you.
I had never heard that term either.
Eyeball planet. I encountered it today for the first time.
Well, eyeball planet sounds much more exciting to me.
Eyeball planet.
Good choice.
Plus
Good
there's
choice.
water there, and that would be cool.
Yeah.
It would be a much more interesting place to set a science fiction movie on an eyeball planet than on a snowball planet. Yeah. We'll come back to science fiction movies in a second. Today we'll have a few more updates from I2 Borisov. It's not Me Too. It's I2. And we'll be talking about Einstein's special theory of relativity and the strong nuclear force, plus the potential long-term hazard of asteroids migrating onto Earth-crossing orbits from Jupiter's private reservoir of asteroids, the Trojans. So we'll talk about the Trojans, and there's a mission that's getting ready to go to the Trojans, which we heard some about at last week's planetary science meeting. But first, this episode of Walkabout the Galaxy is brought to you by quantum mechanics.
Ooh.
Are your electrons causing you problems? Molecules misbehaving? Photons freaking out? Are your Fermi levels off kilter? Bring them down to quantum mechanics, where our team of expert technicians has a reasonable probability distribution function of getting your misbehaving quantum particles working again. At quantum mechanics, you can confidently leave your quantum problems with us, and before you can say Heisenberg uncertainty principle, we'll have your fermions spinning like a quantum top. Quantum mechanics. Impossible is nothing.
I like what you did there. That was clever.
Okay, thank you.
That's clever.
Very nice.
I don't get such praise very often. Thank you.
Yeah, we're so nice.
Well, it was good.
Impossible is nothing?
Oh yeah, I've heard that, but I don't know.
You have heard it?
I have not heard that.
No, any ideas what impossible is nothing, where the quantum mechanics folks might have co-opted that from?
Sounds something like it'd be IBM or something, but I don't know.
IBM.
It does sound IBM-y, but it isn't. Think more biological than mechanical.
I don't know.
Oh, nobody
Pharmaceutical.
cares. Whatever, it's shoes. Adidas.
Oh, I would never, ever get that.
Not biological.
It has to do with
You're on it.
high
That's a
performance
stretch.
humans instead of high performance computers.
Okay. Fair enough.
What I was thinking of. So on the nerd news front, the new space sci-fi movie Ad Astra is out.
Brad Pitt is gorgeous.
Nice. That was a
We
great
know you
segue.
we know you have a man crush on Brad Pitt.
Dude, he just keeps getting better looking. What's the deal with that?
Yeah, well, it's like me.
That's not fair.
Yeah.
I know I've
Psych.
fallen off a cliff as far as how good I've looked. And Brad Pitt, he just keeps going better and better and better.
I'm glad you said something. 'Cause,
Yeah.
Yeah, we have been noticing. Yeah.
But none of us have seen
everybody's
this movie.
talking.
But we should. I hear that it has to do with the Brad Pitt is an astronaut, and he goes up for some long space mission. It has something to do with
Is
the
he by
psychology
himself?
of some. I don't know, But it's about the psychology of long-term space flight or something like that.
I think it would be pretty unhappy. That's it's my prediction.
Yeah,
We're gonna
like
find
it's not
out.
a comedy.
It's
I
not a comedy.
don't think it's a comedy.
It's not a comedy. Although that can also be, because like Misery is a great terrain for comedy.
Mm-hmm.
So maybe somebody should make a slapstick comedy about a lonely
A laugh
astronaut.
track.
Well, we've talked previously about some of the older sci-fi shows that involved. Is it Red Dwarf? I think was the British. Did you watch Red Dwarf, Stephanie?
No.
What shows do you watch?
What shows do I watch?
Like sci-fi shows.
I'm bad about that. I don't really watch sci-fi shows. I know, and you invited me on the show and everything.
You're such like a nerd in many respects, but not.
I mean, not that type of nerd though.
What kind of nerd are you?
Well, like Magic the Gathering.
Okay, that's
Pokemon,
good.
video games.
It's really a score to get Stephanie here today. Today is a Friday, and a new set of Magic the Gathering cards is being released this evening.
True.
And so the fact that
Yes.
Stephanie is here today.
Yeah, I had the choice of that and also playing the new Link's Awakening game too that I recently
Really?
Oh,
downloaded.
she's also.
We're honored. We're honored by your
Yeah,
presence.
you're really welcome.
Does this mean you're not going to the Magic the Gathering release tournament tonight?
No.
But you could. I mean,
But I
we're
could.
not really preventing you from that because doesn't that start at like 7 or something?
No, I'm just not going though.
But you could have gone.
But I could have gone.
You were not really stopped. Are you going to that, Jim?
I
Because
am
you're
not
also
going.
a Magic the Gathering.
Jim usually beats me at those things, so.
No, well, they're too late. I mean, they usually
Oh yeah,
start.
I'm too old for it now because it's a midnight. Is
They
it
used
a
to.
midnight
They used to start at
pre-release?
midnight. I think there is one at 7:00 tonight for us here in Orlando, but they usually start at
It's-
midnight, and
yeah,
like
on
they're
Fridays,
super
it's pretty
crowded,
much
and
always-
it's like a whole thing.
And people
Who
smell.
can start a thing at midnight? It lasts like
Yeah,
3,
no,
4,
I-
5 hours. That's crazy.
So, couple of things. First, Magic the Gathering.
Yeah, nerd.
Oh yeah.
Magic the Gathering is a customizable card game. It's likely that many of our listeners know what that is, but it's also guaranteed that some of them do not.
Right.
Correct.
It's a card game that is what's called customizable card game. It was the first, I think, really. It sort of invented the genre.
Right.
And in the early and mid 90s, there was an explosion of customizable card games where there's some sort of basic set of rules, but then there's an ever-growing reservoir of cards that eager card nerds such as Stephanie and Jim can purchase to the great delight of the owners of the card company.
Oh my gosh.
That
So much
are
money.
like characters that can play in the game. And I got deep into Star Trek customizable card game in the 90s and early aughts until that sort of went under. But that was a whole big thing. Like I was a judge at the 2000 World Championships of the Star Trek
Nerd.
customizable card games.
Awesome. I was never aware of the existence of that. I think I would have been into that for sure.
It was
had I been
awesome.
aware.
impressive.
It was
Yeah.
totally awesome. But speaking of who starts things at midnight, my current hobby is not customizable card games, but I run after a fashion, you know.
Hey, you
and
run fast.
so I pay some attention to professional running and things like that. And the World Track Championship, I think, is happening now, but in a very hot location in the Middle East.
Oh my
and it's a
gosh.
big sort of it's a big deal. And so the marathon starts at midnight
Oh.
Wow.
because
Because
it's
that's
so
the only
hot.
time it's cool enough.
That's
to...
the best chance to not have the athletes dropping dead.
That sounds terrible.
Speaking of the Middle East, our space news, the first astronaut from the United Arab Emirates is now on the International Space Station. Huzzah, which sort of sounds like heroic
Yes.
or celebratory. Huzzah al-Mansouri is on the ISS. UAE has actually been going kind of big into space. They spent a few $100 million on their space program last year, including they're building or financing a mission to Mars, which is being launched next year. University of Colorado lab where I'm from is building a significant portion of that mission. Berkeley and I think Arizona are the other ones. That's called HOPE, and it's being launched on a Japanese rocket. And speaking of, so this Huzzah al-Mansouri is not technically a professional astronaut. He's a paid visitor to the ISS. And so he bought his, paid Russia for his ride up, and he's staying up there for a month. But they're doing some experiments, connected with schools in his country. Nano Racks and Virgin Galactic are both setting up shops in the UAE. So they're sort of looking to the future.
Getting into the business.
Right.
Getting into the business and looking to the post-oil era. And,
Right.
And so...
Right.
Well, this is good. I mean, the International Space Station has, for a long time, just been the United States and Russia. So it's nice that it's now truly becoming international.
And NASA earlier this summer announced that they will allow companies to bring tourists to ISS,
Wow.
and NASA's fee will be $35,000 a night
Oh.
for.
There are places on Earth that cost that. That's
right,
but just getting there.
The
right?
challenge is the challenge will be the ticket to get there.
Yeah.
Right. So
Right.
the hotel fee itself
Yeah.
isn't that exorbitant.
Right.
Right.
Stunning views, maybe not the greatest
It's
accommodations.
like a hostel. or something.
Yeah, it's more
It's like staying at
hostel style.
DPS.
Yeah,
Yeah.
you got to sort of like sleep in a bag with a bunch of
Right.
other people in the same room, kind
Yeah.
of.
Yeah. Yeah.
Right.
Yeah.
At least they're all
Yeah.
fancy people.
Yeah,
It's
yeah.
important.
Yeah. But you do have stunning views, but not. And weightlessness, I guess, makes for a very comfortable mattress
Oh,
because
I never thought about that.
you're not really in contact with anything.
I think that would be off-putting enough that I'm
Yeah.
not sure.
I don't think
the
I could
comfort,
sleep.
Yeah.
Yeah.
I remember hearing that shuttle astronauts at some point had to have things keep them from just like nodding off when they were doing these sort of very long, repetitive maneuvers or something, because on Earth, if you start to nod off, you're literally nodding off, because as you
Right.
start to fall asleep, your head drops forward and that wakes you up.
Yeah.
But in weightlessness, that doesn't happen.
Oh, wow.
Ooh.
So you're just like sitting there, you're just like, I'm
And you can
sleeping.
just sleep. Yeah. Huh.
That's cool.
Yeah. And also, speaking of tourism, are you too familiar with the Starlight Foundation?
No.
No.
They designate official places where you can still go and see the night sky.
Oh, I've heard sort of this
Yeah.
before, yeah.
And so that's becoming a more and more challenging thing,
Yes.
and people are more and more interested. It's like, oh, I would like to see the Milky Way, perhaps in my lifetime.
It's very sad that we can't in most of the
Yeah.
United States.
And honestly, I don't think I've seen it in decades myself,
Whoa.
and I'm only decades old.
Yeah.
So, yeah.
Wow.
It's very sad.
Yeah. Yeah.
So the Starlight Foundation identifies Starlight tourist destinations. They just identified a new one in Portugal, and they also look at things like good hotels and restaurants nearby for your daytime
Oh, okay.
It's good to know.
dining and things like that. And my mother has decided she really wants to see the Milky Way again. I'm sure she saw it
There
also
are-
decades ago, so she's headed off to the desert Southwest.
Yeah, I was going to say, I mean, you can do it in Florida. There's not a lot of places.
Like in the swamp.
The Everglades, the Ocala National Forest. I mean, you have to go
but
far
it's not,
out there, and it's not
as good.
It's not as nice,
because
and it's never going to be as good, right? 'Cause-
Right, the air is not as dry or
Right.
still
Right.
as it would be. Yeah. So sciencey stuff.
Science.
Yes.
Oh, we're all about that.
Science. Yeah.
So we got what do we got? A few things today.
Well, let's start off with this thing about special relativity and the Large Hadron. Is it Hadron or Hadron? I
Oh
know
my
you
gosh,
always
you're going to get it
got
wrong. You get it wrong every time.
The GIF or GIF. Right? I don't know.
What do you think it is? If you had to guess.
For the LHC?
Yeah.
Hadron.
Yeah, she's right. You're wrong.
Yes.
I asked.
Rare.
I didn't make a pronouncement this time.
Oh,
Yeah.
I think you did.
You did.
It's fine. I won. You lost.
Yeah.
I did not. I said Hadron or Hadron. Which is it?
It's Hadron.
Whatever.
So yeah, Large Hadron Collider is largely famous for smashing protons together to see what comes out of those collisions. But it turns out there are other things you can learn from it as well. Just the job of speeding up a proton to some ludicrously high speed causes some weird things, and it causes matter to go into weird phases. So there's a new phase of matter we're going to talk about.
Right. So we've talked.
Cool.
We've frequently talked about general theory of relativity. G
Sure.
equals 8 pi RT. Right.
Constants
Sure,
in
you
there,
got it.
right?
Yeah, there's time and a G in there or something, which describes how matter shapes space-time, and I love it because I don't understand it at all. And Einstein's special theory of relativity is really a very different sort of thing. I mean,
Yeah.
it sounds like they're related, but their relationship is kind of tangential. to each
In a
other.
sense. I mean, the special theory of relativity was the one that came first, right? So this was 1905.
And it's
Einstein's
special because
grandeur.
it's the special case.
Right, it's the special case of your velocity is constant. So it relates what a person in one frame of reference would see compared to somebody else in a different frame of reference that was moving with respect to the first one. So that's the special theory of relativity. The general theory was meant originally just to be, let's generalize that, so you can be in any frame of reference,
right.
speeding up or slowing down or turning, and it turned into a big giant theory of gravity.
Right.
So it's not thought of in a similar vein as the special theory, but really it is the general case.
His approach was, let me generalize this to non-constant velocity.
Right.
Yeah.
And it turned out that had to do something with gravity, which is at first not obvious, but and not even to Einstein obvious, but eventually came out. But today we're not talking about general relativity. We're talking about special relativity, and just weird things that happen to protons when you speed them up to ludicrous fractions of the speed of light.
Right. So by ludicrous, you mean almost 100%.
Almost 100%, right? So remember, one of the tenets of special relativity is that you cannot accelerate something to the speed of light. The speed of light is the speed limit for the universe, and you're only allowed to go that fast if you are massless, meaning you're light or something like light. So if you're a proton, you just can't get there. But you can get to 99% or 99.9% or something like that.
Keep adding nines.
You keep adding nines. You just can never get to the 100. But
yeah,
if you keep adding nines...
If you remember, we had a past sponsor of the show was the Oh My God particle, where we had an argument about how accurately they could know how many nines there were, but it was on the order of 20 nines or something after the decimal point.
Yeah, a lot of nines.
For a cosmic ray proton that was traveling very, very close to the speed of light.
But the cool thing is you add more nines like this. The closer you get to the speed of light, the weirder things get. Special theory of relativity predicts some very weird things happen when you approach these very high speeds, or when you get to these very high speeds. So one of the things that happens is called time dilation. We probably mentioned that on the show a few times, whereas moving clocks run slowly.
This is what happens to my students in my class. Time dilation.
Yeah, unfortunate.
They're sitting there and it's like,
yeah.
It's
How could
only
this
been 10
can't
minutes.
be?
Will he ever stop talking?
And another thing
also
is...
to listeners of this podcast.
Oh, ouch.
Wow.
Another thing that happens is length contraction. That is, if you're moving, you shrink along the direction you're going. And both of these things play into this cool new phase of matter that's called a color glass condensate.
Color glass condensate.
That's right.
That
what
sounds like
mean?
You just made that up. So
I did
we'll
not.
come back
It sounds
to
kind of
that.
made up.
That sounds like an eyeball planet.
Yeah, it doesn't sound sciencey enough.
It doesn't, but it is.
Well,
so,
it sounds like three kinds of science mixed up incorrectly.
Yes.
Right. The reason we say that is a fun thing. So take a proton and speed it up to near the speed of light. What happens to it is it shrinks along the direction it's going. And what is a proton made of?
Oh, we'd have to go down to our friends, the quantum mechanics, and ask them about that.
Yeah, but you should know that because it's...
You guys, it's you guys,
quarks.
right?
Quarks.
I don't get a special particle name, so I don't know, right?
Do you want to be a quark? We've got
a few left.
Bottom rotates,
sure.
and up and down.
Up and down you still have.
Okay, I'll take down.
Down.
You're down with down
That's kind of
quark.
sad.
Yeah.
Oh,
Yeah, I'm kind of sad.
Sometimes she's sad.
No, you're not.
Right, well, I need something
I
to
hope-
counteract my
All right,
happiness.
so she's down quark.
Okay.
So, and up and down quarks are, of course, what protons are actually made of. So
Up and down.
she's part of our discussion. We are not.
Perfect.
But what holds those things together?
Gluons.
Gluons, right? So gluons, excellent job.
Jinx.
Gluons are the kind of force-carrying particles that carry the strong nuclear force. That's why we said at the beginning of the program, talk about strong
And
nuclear
are they
force.
really particles, or are they quanta of energy or is there even a...
They're the same thing. That's the same thing. They're particles the same way that a photon is a particle.
Right.
In that they don't have mass, but they but they're force-carrying particles.
But do they never exist independently of their quarks, do they? Are they really like photons? Can they?
Yes.
Or do gluons go zipping across the universe at the speed of light?
They generally not, but that's just because
Generally
gluons...
But if you get them really upset, maybe they will, or
Well,
something?
no. Gluons like to glom onto each other as well as quarks, and if you try and separate them and get a gluon by itself, they really resist it. In fact, they resist it so much that the further you separate them, the more energy you have to give to them, and if at some point you give them so much energy that they...
How come the universe isn't just a giant wad of gluons then? If they love each other so much.
They love each other so much. Well, because the force only acts over a very small distance, and so quarks that are far apart from one another don't care. Gluons that are far apart, but if you're once they're trapped into like pairs and things like this, and
but you never
the
get
quarks
like
are
a
trapped.
giant,
You just can't separate them because the.
Can you ever get a giant ball of a gajillion gluons?
I don't know.
Is that a thing?
I don't know.
Yeah, I should Google it.
We should check that out. I don't
That's
know the
how you
answer.
figure things out.
As scientists, yes,
That's how
absolutely.
Stephanie's doing her PhD.
Absolutely.
Just Googling
She's just
everything.
Googling.
Yeah.
I
Maybe one
How
reference
to
at the end
do
of
a
the thing.
thesis, yeah.
Google.
Well, I said Stephanie was like, we're trying to understand how planets form, so she Googled that, right? And
Yeah.
then she's like, so she's writing her dissertation based on her Google research.
Yeah.
Yeah, there's a lot of bad
Turns
stuff
out
in there.
Wikipedia has a lot of, good stuff and bad.
Yeah.
So anyway, the cool thing that happens if you take a proton and move it really fast is it shrinks, that slams all the gluons together and makes like a wall of gluons. And the
There's
color
gluons
part
that are in it.
that are in the proton.
And how many gluons are we talking about?
So just a handful of gluons, but they kind of come together and make this wall of gluons because you smushed them together so much. The color
But-
part of the color glass condensate is...
That's from our frame of reference. They're
Right.
smushed.
Right, that's from our frame of
the
reference. From their
protons,
frame of reference,
everything is normal. But the collider that they're flying through
is really tiny.
is
very short.
shrunk.
That's right. So to us, they're smushed together, and as they're smushed together, so the color part of the colored glass condensate is gluons have this extra kind of like charge that's analogous to electric charge, except
But it's not electric charge.
And so we just call the various, instead of calling them positive and negative, the charges, they're different colors. There's red and blue and green. So that's the color part of it. And then the glass part is, glass is a weird substance, right, in physics. Glass is like, it's a solid,
But it flows.
but it flows. So over short periods of time, it's a solid. Over long time scales, it's more like a liquid. And these gluons are similar. So they move around a lot, but if you time dilate them, then it's like they're frozen, right? Because it's
Time is passed. They're moving very quickly.
so for us, we're watching them and we're seeing their time run very slowly. So
Right.
now it's a bunch of gluons that are packed really close together and they're barely moving.
So they become a glass.
So they become like a glass. And this phase of matter is something that we've predicted to exist for a long time but haven't been able to see. But the Large Hadron Collider is providing us opportunity to actually see this stuff for the first time. And that's what this new result is all about. Kind of neat.
Nice. Are there any implications of that on the spot? Put you on the spot
No,
there.
it's just like it's a nice, it's just a nice test of quantum chromodynamics. Quantum chromodynamics
Right,
is
more
the
color stuff.
chromodynamics. I don't know if I said that right. Quantum chromodynamics is our theory about how gluons and quarks work, and it's a prediction of that is that this thing should exist, and if it does, that's just more success. I don't know if there's any great cool technologies on the horizon because of that, but you never know. You never know what we're going to do with that stuff until we get a better handle on it.
Check with the good folks down at Quantum Mechanics.
That's right. That's right.
We have a special Top Quark trivia
All
this
right.
episode.
All right. So, speaking of special relatives, so we talked about this on a recent episode, but I'm going to get your guys' ideas about this. So, say I want to go to Sagittarius A star,
Okay.
which is,
The center of it's the big black hole at the center of the Milky Way.
and I do want to go there, don't you? That would be really awesome.
It's a long trip.
You
It's
can't
a
come
long
back
trip.
from that.
But that's the thing. So it's about 26,000 light years away.
Okay.
Is the center of our galaxy. So the question is, at what speed would I have to travel in order to get there in a year?
Oh, well, I mean,
So the answer is, of course, near the speed of light.
yeah. Are you going to give us a multiple choice?
Well,
or
I'll give you a multiple choice.
calculator?
Yeah.
I'll
yeah,
give you a
Josh can do it in
multiple
his head.
choice.
I'll
The question
yield to
is,
him.
I'll give you that it's at least 99% the speed of light,
Okay.
and there's at least 1 9 after that.
And the question is how
The question
many
is
nines?
how many nines?
How many nines
How many
after
nines?
that to go 26,000?
So what percentage of the
years?
speed of light do you have to go to take? See, this is the awesome thing, right? So it's 26,000 light years away. You say even light traveling at the speed of light would take 26,000 years to get. And it would from our perspective on Earth.
Right.
But if you're in the spaceship going there,
Right.
it doesn't take that long because to you, you're not moving. It's Earth and
Right.
Sagittarius A star that are moving, and so the distance between them shrinks, and so it's not really very far. It's not 26,000 light years. It's some much shorter distance.
You can think of it in the length contraction way, but you can also think of it in the time dilation way, because those things are all
interconnected.
Up.
They all have to work together.
It's still 26,000 light years, but your time is passing more slowly for you.
That's right. Yeah. So that's the question. And there's a second question, just because I wasn't sure if that was a good question. It's probably not, but who cares?
Yeah, love it. We love that question.
The best question I've ever heard.
Here's the other question, which I think you guys will know the answer to, but I'm not sure that all of our listeners will.
Right. Don't blurt out the answer, Stephanie.
Don't blurt out the answer. Einstein is given mad props for special relativity, yes?
Yes.
Oh,
shoot, I blurted it out.
Damn it.
How could you do that?
But it turns out that he didn't come up with any of the math, right? He interpreted a bunch of math that was already around. Mm-hmm. So your question is, who came up with that math?
For special?
For special theory of relativity.
I think I know that.
I think you do. But we're going to see if Stephanie does. We're going to see if our listeners do. So we'll save that.
I think I know that.
All right. Yeah. We'll see. Yeah, we're going to put her on the spot, see how much physics.
Okay, so before we get our answers, our more sort of terrestrial science topic was just about a study talking about some of the dynamics in the solar system with asteroids. We're talking about a little bit about I-2 Borisov. Oh, and I teased at the top of the show, you were saying we're going to have the opportunity to learn how comets around other stars may differ from comets around our own.
Yeah.
Because now one of them is paying us a visit.
Awesome.
We just saw some of the first spectral studies of this interstellar comet with the detection of cyanogen, which is a simple carbon-nitrogen molecule, which is also commonly found in our own comets. Anyway, so far we don't have a lot of information about it, but we're not seeing anything that's dramatically different so far, but there's going to be a lot more data over the next few months through a lot of 2020, but its closest approach to the sun is in December of 2019. And the sort of overall color of this interstellar interloper is consistent with stuff we find in our solar system, but that's not really saying much anyway.
So how, I don't know if you guys know or not. I have no idea. So how precise can the data get? So that is, it would be surprising if it looked radically different from our comet. So it's not surprising at all that it's generally similar, but it should have slightly different like isotopic composition and things like that. So slightly different isotopes of slightly different elements are in different concentrations. Are we going to be able to determine that? Can you do that without like taking a sample of it? Can you do that remotely? I don't know the answer.
Yes, although I don't know from ground-based telescopes the full suite of measurements that they'll be able to make, but our own family of comets has scatter, like they're not all identical.
Right.
And there's this variety of measurements, and here we just got one visitor.
Right.
And where is it going to land in all the various measurements that we make of those things? I don't know. Do you have any bets or predictions about what we'll see from I-2 Borisov?
Well, I hope that it is radically different from what we have.
Yeah.
But
That'll
probably won't be.
Yeah, I don't think it's going to be radically different. But I bet there's some subtlety. I bet we find some ratio of some isotope that's different enough from our continuum of things.
Figure out somehow or something.
Or from a star that has had a different composition in its solar nebula or stellar nebula.
So hopefully,
I think that's a neat possibility.
You get the best data from a spacecraft that can actually go there. And
so we should make a mission right now.
So
that's a quick turnaround. We can do it.
Yeah, we can do it.
Well, one of your many projects that you've worked on during your time here was sort of designing, in some sense, a mission of your own. You want to say a little bit about that?
So I was in the 2018 JPL Planetary Science Summer Seminar, where early career scientists and engineers get together and we come up with a mission concept that is based on what our decadal survey, basically the huge Bible of all of the interesting science that planetary scientists want to achieve in the decade. And the third highest priority for one of the biggest mission class of NASA was a Uranus orbiter, and we sought to come up with a cheaper version of that because the budget available for those missions might not be available. So
so why go to Uranus?
So Uranus is awesome. The last time it was visited by a spacecraft was by Voyager 2.
Yeah, January 1986.
Right, like 30 years ago.
That's when I was in grad school.
So it's a specific type of planet called the ice giants. but it's not really like the snowball planets that we had talked about earlier.
Right, we call it ice giants, but not like the...
Right, it just has methane and ammonia and things like that inside of it. So yeah, it hasn't been visited, hasn't gotten a lot of love like Jupiter and Saturn have with Cassini and Juno. And it's...
Poor Uranus.
Poor Uranus.
I do feel
and
bad for those
Neptune.
guys. Yeah, I mean, every time
Do
I
you
teach
really?
about these, yeah, because both, Uranus, Neptune, it is weird. They're a very different kind of planet, but we haven't,
Right.
and Voyager that you mentioned that went by, that was just a flyby, right? They were
Right.
whipping by really fast and got a handful of images and a handful, of
Right.
the moons and various
With
other,
sort of like early 70s technology.
right, exactly.
Exactly.
So
Right.
let's get back there.
Yeah, and its magnetic field is super strange. Uranus is tilted over on its side. It has one of the most complex geometries for its magnetic field.
Yeah.
It's the only planet that is consistent with having no thermal heat output, essentially.
Oh.
And that is consistent with the giant impact hypothesis. It is thought to have made it turn over on its side. But it's still a really interesting case study, and the fact that it's turned over means it's getting some weird solar input that could help us better understand extreme planetary environments.
Cool.
Uranus is awesome.
Yeah, it has a bunch of rings. I did my PhD dissertation on the data from the Voyager 2 flyby
Right.
at Uranus. Yeah,
Nice.
way back when. So yeah, I got a special fondness for it as well.
The most recent, 2019 Planetary Science Summer Seminar actually was on designing a mission to go to Oumuamua.
Oh,
Right.
really?
Yeah. I don't
Catching
know.
it somehow?
Yeah. So hopefully,
What?
and I think they're working
Isn't that
on.
flying out of the solar
Well,
system?
they
at
had
ludicrous
help
speeds?
from JPL's Team X and Team A, so they came up with something. I'm
To
not allowed
go-
to say any more about it, but
To go flying off and catch this interstellar thing so that's on an escape trajectory from the solar system.
right.
So that requires some speed.
Hmm.
So
I would not have thought that was a
A
technologically feasible
Yeah.
thing.
And
Yeah.
within New Frontiers, I think. So that $1 billion
Wow.
class mission.
Yeah, not going to happen.
Yeah,
But
not gonna happen.
that's
But
a cool
a Uranus
idea.
mission,
Uranus mission
Yeah.
probably will happen at some day if we're still around.
it's got to happen soon.
Awesome.
Yeah. So this new thing has to do with Trojan asteroids. So just as a reminder, most of the asteroids, well, we frequently talk about near-Earth asteroids, which are ones that are on Earth-crossing or potentially Earth-crossing orbits. The bulk of the asteroids in the solar system are sort of safely orbiting between the orbits of Mars and Jupiter, what we call the main belt. But there's two fairly large populations of asteroids that sort of share Jupiter's orbits, and they're called the Trojans. And they're orbiting the Sun at the same distance from the Sun that Jupiter is, but at different locations along that orbital path. And there's a sort of interesting quirk of orbital dynamics that says that an orbiting object can sort of trade off how tilted the orbit is with how egg-shaped it is, depending on the sorts of perturbations it gets from other objects, so the other planets that are in the solar system. And a lot of the Trojan asteroids are on relatively inclined or tilted orbits, and there's probably a significant number of those that haven't been observed or discovered yet. And if they go through this sort of eccentricity inclination trading, the tiltiness trading off with the egginess, if they become more egg-shaped orbits, if you're out at Jupiter, that can bring you in close enough so that Mars then can tickle your orbit and change it in such a way that it
Tickle
eventually
your orbit.
becomes...
Josh. I have a question about this I don't understand. This is genuinely me being stupid, I guess. I thought if they shared the same orbit as Jupiter, how do they have very tilted orbits? Jupiter's orbit is not very tilted.
Right. So when I say share the same orbit, I really just mean share the semi-major axis, which is the mean distance of the object from the Sun. So the orbital period is the same. And so they're in what we'd call a one-to-one resonance with Jupiter, so that they're in some sense protected from colliding with Jupiter in these Lagrange points, but there's some flexibility, as I understand it, what the inclination is, because the inclination and which is the tiltiness of the orbit, and the eccentricity, which is the egginess of the orbit, are not tied to the orbital energy.
Right.
And so these things have the same orbital energy as Jupiter, meaning they're on average the same distance as Jupiter is from the Sun.
Mm-hmm.
Did that
Interesting.
answer your question?
It did, but it's new and interesting. I did not realize that. I thought they were just all locked in the same plane as Jupiter. And
No, yeah, they're bouncing around, and there's most of them that we've seen at least are, but they can be a significant population up to inclinations. I think they were seeing as high as 40 degrees, which is quite a significant tilt.
Yes.
There was a mission in the works, a NASA mission, a discovery mission, along Stephanie was just talking about potential discovery mission to Uranus. One of the discovery missions in the works with NASA is called Lucy, and Lucy, wonderfully, is not an acronym. It's just a name.
Nice.
Acronyms are great, though.
Acronyms. Sometimes it's nice. We don't have to give everything an acronym. We just give things a name. And
Right.
Lucy is a name, and it's inspired. Do you know what it's inspired by?
The human.
Yes.
Not, I don't know the word for it, but yeah, one of the first
proto-human
pre-human,
thing.
proto-human.
Yes, the hominid.
Hominid.
Lucy.
Yes.
That was a couple million-year-old fossil
I
remains.
couldn't think of the name for it. Yes,
Yeah.
but one of the first types of humans.
So that was sort of a ancient, it's a discovery of a sort of fossil that tells us something about our origins, and the Lucy mission is named after that because going to the Trojan asteroids, those things are far enough from the sun that they've been less altered by the heat from the sun, and so therefore they would have sort of fossilized information about conditions at the formation of the solar system. So that's the reason behind the name, and our friend Hal Levison at the Southwest Research Institute in Boulder is the head of that mission, which will go out and explore, I believe, 7 different asteroids in the Trojan populations near Jupiter. That's launching sometime in the 2020s and finishing sometime in the 2030s. So that'll be a cool thing coming up. All right, you want to take us back to your 9s?
All right.
Oh, man.
So I want to go to
at random.
Yeah, that's fair. It's random.
9 nines.
I really want to go to Sagittarius A star, 26,000 light years away. At what speed would I have to travel to get there in 1 year, assuming that I could instantaneously accelerate? I guess I didn't say that first time, but of course
Right.
it would
Just
take a really
assuming-
long time actually to speed up and
that
slow down
you're-
from that. I'm assuming I can go from rest.
It's a special theory of relativity case, so there's
Right.
no acceleration.
There's no acceleration. I just go instantaneously
Yeah.
from rest to whatever the speed is, 99 point some number of nines
Okay.
times the speed of light.
Stephanie,
How many
you
nines
want
do I
to
need?
How many nines did you need?
After the
decimal
decimal
point.
point.
I mean, there's definitely some equation that I've just forgotten
Yeah.
to use, but I'm gonna just guess at random.
Yes.
Okay.
that's
I'm
what
going
you
to
should do.
say 3 nines.
3 nines.
Oh, that's a very good guess, I think. Because I was either going to guess 3 or 4. And the reasoning is you're going 26,000 in 1. So the contraction scale is about 10 to the 4, 10 to the 5. And so the equation you're thinking of has square root of 1 minus v squared over c squared. And you do some kind of Taylor expansion on that or something or other. It's something like v over c, and you want a time savings. Oh, I'm so excited, I can't speak anymore.
Okay.
You want a time savings of something like a factor of 10 to the 5. So that I think it's something like 99.999%. That'd be my guess.
All right. They're both going with 3 nines. Nice. The actual answer is 7 nines.
I was closer with the 9 nines.
Yeah, you are closer with the 9 nines.
Darn.
So 99.9999999C.
So the extra is because I did my squaring or square rooting wrong.
I picked
Possibly.
randomly wrong.
Yeah. Interestingly, by the way, if you wanted to go at that speed to the most distant galaxy known, it would still take a long time, 500,000 years. So what about the other one? Who came up with all of the math that goes along with the special theory of relativity?
I'm really bad at people's names, honestly.
Double points if you give the first name also.
Oh.
Yeah, Josh knows probably. I have no idea.
You have no idea. You're
No
not gonna
idea.
hazard a guess.
No idea.
It's
Okay.
Lorentz, right?
It is Lorentz.
Yeah.
All right.
What was his first name?
Oh boy.
Come on. Our listeners are going to beat you. They know the answer.
Yeah. Oh,
At least
shoot,
one of them.
I'm very embarrassed.
It's okay. It's
I'm-
okay.
I'm
No worries.
embarrassed too. Give me that first initial.
H.
Well,
I don't know.
it's not Hans, is it?
No, it's not.
It's
like Harold.
Yeah.
oh man, I don't know.
It's Hendrik. Hendrik
Yeah.
Lorentz.
I was not going to get that.
And thus the transformations where you go from one reference frame to
Alright,
another
that
are
makes
called the
sense.
Lorentz transformations, and they
Right.
were discovered not by Einstein, but
Right. By
kind
Lorentz.
of
Written down by him.
written down. Yeah, I mean Einstein identified what they meant, right? He that's the hard part.
Gotcha.
Lorentz wrote all these things down, but didn't really believe
together.
put it together that actually meant that time ran differently for different things. You know, that's conceptually a very hard thing to accept as true.
Right.
But Einstein had the imagination to do so.
I'm still trying to figure out what my head math error was with all the nines. So it's really 9 total nines. It's 0.9
Right.
with 9 total nines, and the square root of, so that's the 4.5. I think I took the square root when I shouldn't have.
Right. Something like that.
So it's really 9 nines, and I was
He
thinking,
almost was there.
I
and
should
I
have
was
stuck to
thinking
my
it's
gut.
4.5.
9 nines.
Yeah.
So the 3 after the decimal's like 5 total, 4.5. Yeah.
Yeah. Well.
Okay.
Pretty fast
Shoot.
is the answer.
Yeah.
Shoot.
And I was gonna ask how long you would have to accelerate at g to get to that speed, but then I couldn't
Oh.
calculate that in time because it was too close to recording time.
Yeah.
Anyway,
While it may have felt like the time to fly to Sagittarius A-star, it was just another episode of Walkabout the Galaxy. If you like this episode of Walkabout the Galaxy, write us a review in whale speak and build a giant interstellar probe like the one in Star Trek IV, The Voyage Home,
awesome movie.
which kind of looks like the artist depictions of Oumuamua.
Ah, that's true.
If you think about it,
Yeah.
like a big, long, sort of cylindrical, black,
I
metallic
didn't
kind
realize
of
that was
thing.
nonfiction, but it
Right.
was.
Clearly.
Right. That may have been a whale probe coming here to save the whales. And send it off to save the whales and plug our podcast. If you didn't, try putting it on autoplay while you're sleeping. Be sure to like us on Facebook to get all our updates, and check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walkabout the Galaxy, where you can see the computers running the simulations of podcast hosts. We're not really here. Catch up on old episodes wherever you get your podcasts, thanks to our listeners in the undergraduate room in the physics department at the University of Central Florida and around the world. Follow us on Twitter
At walk_the_galaxy.
and ask us questions anywhere using hashtag #WalkaboutTheGalaxy. Our theme music was composed by Richard Jerusik. Thanks again to Stephanie Jarmak for joining us this week.
Thank
Thanks,
you.
Addie Dove will be back on the next episode. I'm Josh Caldwell.
I'm Jim Cooney.
We're the AstroQuarks signing off until the next episode of Walkabout the Galaxy. They got nothing. Okay.